Hello, today is the 5th day of this course. Welcome to the course, and what we are going to discuss today is how different types of variational formulations, and one of these particular formulations known as the Rayleigh Ritz method is very frequently used in finite element analysis. But we will not only discuss the Rayleigh Ritz approach, but maybe in the next class or one or two other classes, we will also discuss other approaches which are used to formulate our problems. And the fundamental difference in all these formulations is of two types. First is that either we use the strong form or the weak form, that is one difference. And the other difference is that what type of weight functions do we choose. So, what we had discussed earlier was that the choice of weight functions is to be such that it has to meet, in context of weak formulation, it should represent the variation in the dependent variable. In some formulations, it is a little more restricted. So, we will discuss all these things in detail. So, we are going to discuss variational methods, and till so far we have not come to the element level, but maybe in one or two lectures, once we have covered, we have done an overview of different methods, we will see that these methods which we are discussing can be applied either over the entire domain of the system, or we can apply them at an element level also. So, if we understand these methods, then graduating from here to the element level and developing element level equations is a fairly straightforward exercise. So, it is important that we understand the fundamental principles underlying these methods, and then we will start working on the finite element formulation. So, the first method is known as Rayleigh Ritz method. And in this, couple of important points, that we only work on weak form. Second is that when we pick phi's, so we pick them in the way that u equals phi j, c j, j is equal to 1 to n, and these phi's are linearly independent. We cannot pick up functions which are linear functions of others. Okay. Otherwise, we will get simultaneous equations, n equations in n unknowns, but when we will start solving it, we will not be able to solve the solution unknowns. The third thing is that in Rayleigh Ritz method, W is nothing but phi I. So, once we have made a choice on these phi j's, I essentially use the same functions in place of W. Okay. These Cj's are called Ritz coefficients. They are called Ritz coefficients. So, if there are n unknowns, I know that there are n weight functions also, because the number of weight functions associated with n unknowns is also n. So, I get n equations, n unknowns, and I can solve them. Further, what we had discussed earlier in the last class and the class before that is that these functions phi j's, they have to meet only essential boundary conditions. We do not have to worry too much about the natural boundary conditions, because when we develop the weak form, the natural boundary condition automatically comes into the equation, and if its value is known, we just plug in those values in the equation. And the last and very important point is that all this thing works well only for systems where this B of W and U is bilinear and symmetric. I will not say it works only for, but it works really well, works well for systems. If it is not bilinear and symmetric, then we may end up getting nonlinear equations and C's. So then we have to figure out how to solve them. But for bilinear symmetric functionals represented by BW, it works really well, and it's pretty straightforward. So we will discuss this further. So example. So we had seen that in context of that bar, that is one differential equation it can solve. There may be others also. It could be in general represented as B of W and U is equal to L of U, W. And we say that B is bilinear and symmetric. So if that is the case, then I can also represent it as I equals half of B U comma U minus L of U. And so this is the equation which I have to solve. This is the functional, and if I minimize this functional, I get this equation. We have seen this in the last class, because the variation in U is W. So this is W. Okay. So now we assume that U, and let us say that this U is having n terms in its solution. So that is why I call it UN. So it is an n term solution, Cj, phi j, phi naught is some constant. Okay. So I can, so let us call this equation 1, call this 2. So if we put 1 in 2, what do I get? I get, so UN is this entire thing, U is this thing, and also W is, no, that is fine. But what I am saying is, I know that U is this equation represented by equation 2, and W is the weight function, and I said that in Rayleigh Ritz method, the weight function is same. So it could be, it is phi I. So instead of W, I am putting phi I, comma, Cj phi j plus phi naught. So this entire thing in parenthesis, it represents U is equal to L of phi I. This is equation 3. And we will actually do one example. Right now this is very general, but we will actually do an example, so you will see how this works out. So, because B is bilinear, what I can do is that I can pull out Cj out of this bracket, and we will actually do an example and we will see what that means. So, I can write it as summation of j is equal to 1 to n P of Phi okay. So, because it is bilinear, I can separate this phi naught separately, and also because it is bilinear, I can, oh where did Cj go? Cj. I can take Cj also out of the bracket. Now, when you look at this equation 4, you see that for different values of I, so j is equal to 1 to n. Okay. For different values of I, this is one equation, and on the indice j I am adding up everything, right. So, for different values of I will get different equations. If I put phi is equal to phi 1, I will get one equation, phi is equal to phi 2, I will get second equation, and all these Cj's are unknowns. So, I will get n equations involving Cj's which are n unknowns. So, I will get n equations and n unknowns. Okay. And essentially what I will get is a B matrix multiplied by a vector C, and this is equal to a vector F. So, this is known, this is unknown, and this is known. Okay. So, now I can solve these equations and get the values of C's. So, we will do an example. So, this is which formulation? The Rayleigh Ritz formulation. Okay. The main thing about Rayleigh Ritz formulation is its weak form, it uses weak form, and here the choice of weight function is same as the choice of polynomial approximation functions. So, in context of the bar problem, B we had seen it was defined as 0 to L dw over dx du over dx times dx, and there was this constant a or some parameter a. Okay. So, what we will do is we will compute this B matrix for this type of a function. So, first step is that we say that u is equal to Cj phi j, j is equal to 1 to n, and in this case for purposes of simplicity we limit n is equal to 2. So, the size of our B matrix will be 2 by 2, 2 by 2. Let us calculate how do we figure out what are the terms in that matrix, and then W is phi I, then B of phi I phi j is equal to 0 to L a times So, I am right now just working on the B matrix and I have to sum it up over j is equal to 1 to n. So, this is equal to integral of 0 to L A times d phi I over dx, right, and I have to sum these things on the index g, on the index j, right. So, what do I get? D phi 1, see phi could be 1 and 2, it can have only 2 values, right, because n is equal to 2. So, d phi 1 over dx times C 1 plus d phi 2 over dx times C 2 dx. Agreed? Okay. So, now in this equation I can vary. In one case I will be 1 and in another case I will be 2. I can have 2 values because n is equal to 2, right. Okay. So, when I is equal to 1, what do I get? B phi 1 phi j is equal to 0 to L. So, I equals 1 times d phi 1 over dx times C 1 plus integral 0 to L A d phi 1 over dx times d phi 2 over dx times dx. And when I equals 2, then my B functional is, so here I is equal to, instead of 1, now I will put 2, right, and this equals 0 to L C2, C2. Where should I put C2? And there has to be a dx also here. And actually this should not be, it should be u, because I have this entire thing is u, right, this entire thing is u. So, this is equal to d phi, and instead of, if I is equal to 2, then I get here this thing. Okay. So, I am getting 2 equations. One is for B of phi 1 u and the other one is B of phi 2 u. And now I identify these things. So, what I do before I move this C1, C1 is a constant but it is unknown. So, I move it here outside the integral sign. I moved it outside the integral sign, and then this term is B11. This integral term is B12. This integral term is B21. And this integral term is B22. Understood? So, this is how I calculate the values of B's. I know what kind of P's I have, so I can integrate these and get the entire B matrix, which is in this case 2 by 2. If n was 3, then this B would have been 3 by 3, and so on and so forth. So, my equation is B11, B12, B21, B22, C1, C2. See, C1 and C2 are unknowns. So, these equation 1 and this is equation 2 can be represented by this 2 by 2 matrix multiplied by this column vector, this vector on C. And on the right hand side, what do I get? I get the F equation, you know, the terms involving the F vector. I basically do the same thing on LU, the linear term. I do the same thing on LU, and I will get my F1 and F2. Any questions, confusion? How I get F? Okay. So, this is how we get this B matrix, and then we multiply it by this vector of unknowns, which is the C column, and that equals the F vector. Now, the way you calculate this F vector is that you have to go back to your definition of this LU term, right? Okay. So, that is what we will do in next 5-7 minutes. Okay. So, and for that again we have to go back and refer to the original equation. So, let us go back and see the definition of L. Okay. So, in my definition of L, I have this WA du over dx and also W times Q. Okay. Now, in this case, at x is equal to 0, u naught is, excuse me, at x is equal to L, at x is equal to L, I have specified that this is A du dx is 0. So, this term is 0, right, and at x is equal to 0, u naught is specified. So, W will be 0 because it represents the variation, and because that thing is specified, then it is 0. So, in my L functional, which is a linear functional, only this term will appear, only this term will appear in context of these boundary conditions. If the boundary conditions differ, then it can change, okay, it can change. So, what we will do is, so if I move this to the right side, this will become a positive thing. So, that is what we are going to calculate. So, my linear functional was what? Actually, it was Q times W dx, right, and it has a positive sign because I have moved it to the right side. Now, this will give me the F vector. How do I get F vector for F1? I put phi1 in place of W. So, I get F1 is equal to integral of Q, and I know Q can be a constant or it is a varying function, I do not know, it depends on the nature of the problem, but that is known. So, this times phi I times dx 0 to L, okay. And similarly F2, in this case the choice of W is phi 2. So, it is 0 to L Q times phi 2 times dx. So, here I is 1 and here I is 2. So, these are the definitions of F1 and F2. And what kind of phi 1 and phi 2 I have to choose? Which? These phis have to meet which conditions? The essential boundary conditions. They need not meet the natural boundary conditions. Now, they need not meet the natural boundary conditions. So, that is there. So, this is what I wanted to discuss in this particular example, and what we will do in the next class is we will actually do one more example. So, here, so initially we have discussed everything in a very abstract sense, then we went ahead and actually this is the abstract sense where we said that we will get a set of equations B times C equals F, and then we actually made it more tangible, and for n is equal to 2 we have computed the values of B11, B12, B22, B21 and also F1 and F2, and then the next example we will actually do a real equation and we will solve for some of these terms. Now, two important things I wanted to make. These were, first thing is that if you look at this B matrix and if you look at these terms B12 and B21, they are same, right, because if you d phi 1 over dx times d phi 2 over dx, and here differential of phi 2 with respect to x times differential of phi 1. So, it is a symmetric matrix, and this symmetry comes because our original function B was what? It was symmetric. It is directly because of that reason. Second thing, suppose we had, instead of our weak form was something like this. Suppose our weak form was something like this. Suppose it had a square. So, this is not a linear system, right? It is not a linear system. If that would have been the case, then when we would compute the values of B's and C's, we would not get linear equations in C. Okay. Then we would not get linear equations in C, because when we replace U with Cj Phi, we will get squares and cross multiples of Cj's. You may get C1 square plus C2 square plus C1 C2 plus C3 square plus C1 C3 plus C2 C3 and so on and so forth. Okay. So, these equations will not be linear. These equations will not be linear, and neither they will be symmetric. They are symmetric because B is symmetric, and these equations are linear because B is bilinear. Okay. If they are linear equations, they are very easy to solve. If they are non-linear, then it is a much tougher problem. So, at least in context of the discussion we will be having in this course, we will be only solving linear problems. Okay. So, suppose, so that is one thing. The other thing is that I also had this phi 0 term, this phi 0 term. Now, phi 0 term helps us take care of, so suppose you have a bar and there is a displacement 5 millimeters here, then all these phis, all the values of phi j, it will be 0 at this end and this end, right, that is how we are picking up. But then at the end there is some displacement which is 5 millimeters. So, that is done through this introduction of phi naught. Okay. So, that takes care of the non-homogeneous boundary conditions related to essential related to primary variables, Okay. These phis take care of the homogeneous conditions related to primary variables. We had discussed this earlier. Homogeneous condition means things are equal to 0. If there is a non-homogeneous condition, then this phi 0 term takes care of that. So, that is why we had introduced this term phi naught. Okay. So, but the mathematics is identical. So, we do not have to worry about it, mathematics is identical. So, that concludes our discussion. In the next class, we will continue this discussion and do one or two very practical examples of actual differential equations, so that you become more familiar with this method. Thank you.